Did anybody have any burning questions on the homework? I have not uploaded the key yet, but yeah.
I have a question about question number 4, I think. One with the GEOL expansion of radiation, or not radiation, but flow in and out.
Yeah.
So in the notes, you factored out the constant term
Yeah.
to make the remaining like 1 plus da-da-da-da,
Right.
1 minus da-da-da. What was the purpose of that? Because in the end, it like results in the same thing as if you like ignored it because you assume that the two constant terms.
It doesn't make a whole lot of difference. It's sort of like, how do you find the particular solution? And you can find it either way. It's in some problems it would be more complicated, but in that problem you can kind of approach it, either you can pull it out at the beginning or you can wait until the end and then figure out what it is by matching the initial condition. So in that particular case, the initial condition kind of makes it obvious how you have to do it. But it's still important to remember that it's like, so our general solution would be something like, whatever, something like that. And technically that's not including the particular solution that has something like that, plus T0. Because there's no value of A that makes A, no constant value of A that gives you an extra added bit. So as long as you're not afraid to add this one in the end to make it work, it isn't so bad. But to be really careful, we should formally think of this as being a particular solution and this as being the general solution. So when we match the initial conditions, we're matching both this coefficient and the particular piece. Does that make sense? But we're going to keep solving those kind of equations. Well, we're not going to solve this week. We're going to start talking about how those equations behave. And maybe this will become a little bit more familiar as we think about it kind of from the perspective of describing how the solutions have to behave rather than the details of how you find the particular pieces of the solution. So up until, well, there's a really great book by this guy, Steve Sturgatz. And in my mind, this changed the whole conversation. So Steve Sturgatz, he was a professor at MIT and at Cornell. He wrote some math, like kind of blogs for the New York Times recently. But he's just a very good communicator about how to think about math, which isn't so much how you do it, but it's how you think about what you're doing while you're doing it. And I have been very inspired by his approach in his book that's called like Chaos and Dynamical Systems, I think, or Dynamical Systems of Chaos. But which you can get through the library if you want to look at it. And a lot of the examples I've drawn from that. But the key point he makes is, so last week we basically said, okay, we got this complicated differential equation. Maybe it's nonlinear. Well, we can't handle nonlinear ones, so let's just Taylor series. Then we get a linear system and we can solve them. And then the solutions always kind of look the same. So that's part of the story. But what's the problem with that? Where does it tell you? It tells you about behavior only where? Close to the place where you Taylor expand. Now, away from that, you might also kind of want to know what's happening, but getting the precise number or the precise rate of change far away is really complicated. We talked about how the nonlinear part is like whatever, is often can't solve it directly, we can't solve it by hand, we can't even write down what the solution looks like, but we can plug it into a computer and just solve the equation. So most of the time now, for nonlinear differential equations, if you're doing them in research, you're going to use a computer, you're going to solve them that way. But it's really helpful before you do that to have kind of a general idea what the system's going to do. And so what Strogatz's book does, and what I have tried to mimic a little bit in the notes for this section, is to start to think about that, which isn't so much about here's the formula for a particular solution, or how do we get a solution that when we check it, plug it in and check it, it works, but just kind of how do we draw some really helpful figures that help us understand how differential equations work in general. Okay? And it turns out there are a few figures that if you draw them just looking at the equation, you'll have a sense of the qualitative behavior of the solution, even before you go to a computer and code it up, or before you try and Taylor series or anything like that. And you'll see in retrospect that the stuff we did last week was really building toward the local analysis near steady states, but we're going to think about what happens in the rest of the flow field as well. Okay? So, we're going to think about differential equations, and we're going to start off thinking about, and so, all right, and I'm going to use a little dot. Dot just means d by dt, to just make it faster to write things. So we're only talking about ordinary differential equations, and we can think of our independent coordinate as time if we want, or you could think of it as x if you want to, whatever, it doesn't matter so much. But we're only going to have derivatives with respect to one thing, and we're just going to write them with dots or double dots, just first and second derivatives. And then we're going to think of an arbitrary function which depends on this, maybe non-linearly, and also maybe some parameters. So we're going to have two kinds of figures we're going to draw. We're going to draw one that's basically this side, and then this. And that seems kind of silly, but we're going to be able to interpret that. And then sometimes we're going to look at the steady state part and examine how x depends on the parameters. Okay? Those are the two things we want to get at today. If we do that for a bunch of examples, we'll actually have learned a lot about how to do this. And then next time, we're going to start either thinking about double dot, or maybe you can think about it like this. Let me not write it this way. We could also think of x dot as maybe being a velocity, and then we might have a separate equation for velocity dot that is some other function of x and x dot. Okay. So you could think of this as, this is a first order system. There's just one first order ordinary differential equation. This is actually a second order system. Even though I have only one derivative in each equation, I can substitute into this one and write that as x double dot. So I can either think of it as two coupled. Coupled is an important word. We'll come back to that in a second. Two differential equations that are coupled, connected to each other, or one equation that's second order. So coupled means if I write all my variables that have my time derivative, whatever they are, they're not separate from each other. So we talked a little about coupled algebraic equations and how we use diagonalization to decouple them and pull them apart so that we have separate systems that close within themselves. This is the same thing but for differential equations. So if this only depended on x, and this only depended on y, and this only depended on z, they would be uncoupled because this equation doesn't depend on those. But if this depends on x and y, now these two are coupled. And if this depends on z, now all three are coupled. So it's kind of like on the right-hand side in these arbitrary functions, are we seeing the solutions from other sets of equations? That's what coupled means. Okay? All right, but back to this guy. Okay. So last time we solved constant coefficient linear, so let's do that part first. Here's an example. Absolute value m, but I just have a slope, and I have an intercept. So I have two parameters, r and m. And I want to make a graph that puts x dot up here and x here. And this is a little unfamiliar maybe, because the units of x dot aren't the same as the units of x. It's a little bit crazy. This is called a phase space diagram. We're plotting x together with its derivative. Okay? So you could think of this as position and velocity if you want, but this is more generic than that. Okay? So what does it look like? So this is a straight line. Is it sloped upwards or downwards? Downwards. And we don't really know what it's going to look like, but we can imagine one looks like this. So it intersects at R, and the slope is downward. Okay. So, is there a steady state solution to this system? What does it mean to be steady state? Just thinking about the equation.
Derivatives equal to 0?
Derivatives equal to 0. So this part is telling you that things are changing. If things are not changing, set that to 0, then that other side has got to be solved. Okay, so where is that on this figure? If this axis is the derivative, where is the derivative equal to 0? Just somewhere, any intersection with the x-axis is going to be a steady state solution in this kind of figure. Is that steady state solution stable or unstable? The way to think about that is, suppose we started a little bit above, and so our initial x value, and now we know in our head that we've got initial value, initial conditions going, we've got particular solutions, we've got all kinds of things that could be happening. But we're going to try and just think a little more dynamically. So suppose our x wasn't at a steady state, it was nearby. What does it do? If I'm at this value of x, what's my rate of change of x? Positive or negative? So which way do I go next? This way. Is that true here too? True here? So anywhere, as long as the x dot is below 0, I'm traveling to the left. Does that make sense to everybody? What about where x dot is above 0? I'm traveling to the right everywhere. X dot is increasing. Okay, now is that point stable or unstable? Stable, because if I perturb towards smaller values of x, I come right back. If I perturb towards bigger values of x, I come right back. So, color in stable dots with a filled in circle, just for convenience. Okay? What if I had a different value of r? What would change? Let's just dash one. So now r is negative, but m is about the same. Steady state is moved. Is it still stable? Yes. Still stable because this. Okay, thinking about last time when we talked about the feedback parameter, what here is our feedback parameter? Well, remember we said a positive feedback would lead to an unstable and a negative feedback would lead to a stable. So what in this system is our playing the role of our feedback? Minus m. We've written it down to be strictly minus. So as long as this stays negative, we could have a slope that was shallow or a slope that was steeper, but we're still always stable, coming back to the point. Because the point is always sitting in the origin, and below the origin we're always heading back that direction, and above we're always heading back that direction. We might go more slowly, we might go faster. Yeah?
Just by looking at this diagram, would we be able to tell if it was periodic versus stable?
There can't be any periodic functions in the first order differential equation. Yes, we will do that, but there's not even a way you can imagine it happening, and that's for a good reason. You can actually prove that that can't happen. When we get to the second order ones, we're going to see periodic.
Even if it's like nonlinear?
Even if it's nonlinear. So we can make this line wiggly, because wiggly, oh no, can't make it that wiggly. we can make it any, it doesn't have to have a straight slope, it could still be wiggly, but as long as it only crosses the origin once, it crosses the x-axis once, There's only one stable solution, and all of these are heading this way. Because they're all below, all these are heading this way because they're all above, so it's stable. So this is where we jump from the linear systems to the nonlinear systems. As long as there's only one root, it doesn't really change qualitatively. Though it would go faster or slower depending on those little bumps, it's still always increasing because it's above the x-axis and always decreasing. Okay, so how do I make one then that's unstable? What's an equation that's unstable? It looks very similar. So similar that you actually don't have to do anything.
It's just the same one, but going with the positive slope.
Right, so I removed the minus. And now, whatever R I choose, whatever M I choose, they're all going like this. And each of them would have a steady state where they cross the origin, x dot. And when I'm above the origin, what happens? Move which direction? To the right. So they're all going this way. And when I'm below the origin, they're all going this way. So they're all unstable. So just like last time we talked about the feedback parameter being a negative feedback or positive feedback being negative and positive, here is the same thing. Just all of them, think of them in this figure, it's pretty easy to understand what happens.
Can you go over again how we determine which way the function works?
It's just because I'm plotting the derivative of the function.
Oh, it's just like.
It's just like everything above this line is going that way because the time derivative is positive. So it's just, it's almost like blindingly straightforward. It's so straightforward that you forget that it's that straightforward. It's just because that's what we're plotting. We wrote down the equation and then we're plotting the rate of change and we're plotting the value. Okay? And same thing here, these could be really wiggly, but if they only have one intersection, it's going to be unstable. And qualitatively, they will be similar, even though quantitatively, the rate at which you move away from that fixed point will be different. All right, make sense to everybody? Let's think of them. So, I could also plot a different figure where I look for the steady state value. We call it x star, or we call it xss, either way, whatever you want, versus r steady. So now, what's the equation for the steady state as a function of r? How do I find that?
Well, the steady state is when x dot is 0, so you could.
So I could just say if x dot equals 0, which equals minus mx plus r, that means that r equals mx, or so I can apply it that way. So r equals mx. So it's a straight line going through the origin with the slope at m. Does that make sense? So as I'm changing r up and down, my steady state is sliding around on the x-axis, and this is the line that tells you what it is. And I can do the same thing for this one. I would just get r equals minus mx, so I have a negative slope. So this is called a parameter dependence diagram, or sometimes a bifurcation diagram, for a reason we're going to see in a minute. Because in nonlinear systems, they might be more interesting. Okay, so let's think about our first nonlinear system. Did I even write down the equation? Okay. No. I didn't write down the equation. I just drew it. What if this is x dot, and this is x, and I have a parabola? Do I have a steady state? Yeah. Why?
Because x dot is equal to.
Because I hit a point on the origin where it's equal to 0. And is it stable or unstable? Which way do I go from on this side? Towards positive. But I also go towards positive on this side. So if I displace to this side, I come back to my steady state. But if I displace to this side, I run away to infinity. So I have a half stable point, which wasn't really possible for the linear cases. We didn't talk about the pathological cases of the linear cases. I could have had one. What if I had a line down here? M equals 0 and R is negative. So no steady state. And which way do I move? Always going this way. Because I'm always x dot equals negative. Or I could have had this above and I would have always just moving that way. There's no steady state solution, but I can still talk about the qualitative behavior. Does that make sense to everybody? And I could have the really pathological case where this was my solution. Then what happens? X dot equals 0 for any value of x. Every place is a steady state. There's no dynamical anything. It just sits still. Whatever x you choose, it stays there. It's not a very interesting system, but it also falls in this category of systems. Okay? All right, so we've got a half stable one here. That's cool. So what is that? What's the equation for that? X dot equals, let's say, x squared. That may be a little uncomfortable because the units are all crazy. We could add a coefficient if we want to take care of the units. But the coefficient is just going to change the rates at which we go away. It's not going to change the qualitative behavior. Okay. What if I add a constant to this? What are the possibilities now? What if B is positive? What does it look like? It's like this, right? Here's B. So what's the behavior there? No steady states, and which direction do I go? Towards positive x. No matter which x I start on, I'm always going that way. So it's the same as this line. It just keeps flowing by. Does that make sense, everybody? Okay, what if B is negative?
Yeah, would we care about the imaginary steady states?
In this case, no. And here's why. So, well, you could if you wanted to think about it. If x is observable, then it's not imaginary. And so, in that sense, it's not. So when we'll find imaginary things, it will be in something that's not directly observable. Like an observable number won't be imaginary. It'll be some part of the behavior that'll be imaginary. And so the observable will still be either sine or cosine. But the imaginary will kind of hiding in the e to the I theta. So when we get to imaginaries, we'll see those. But it's a good question. Because you could, I mean, this has also plus or minus I, B as solutions. So that is there. It's not on this figure, but that's possible. Okay. But if we disregard those because we're sticking to x being an observable thing, we don't have imaginary things for x. Okay, what about this one if B is negative?
You have two steady states.
We have two steady states. Are they stable or unstable? Which way do we flow over down here? This way. And this way, we're going this way. This way, we're going this way. So what do I got?
Wait, I'm still a little confused on how you decide which way the arrows go.
Because x dot is what tells me where I'm going next. It's my rate of change of x. And anywhere below 0 for x dot means I go towards smaller values of x. Anywhere that I'm above 0 for x dot, I'm going towards bigger values of x. So it's as simple that every time I'm plotting above the x-axis, I'm going to that way. And every time I'm plotting below the x-axis, I'm going that way. It doesn't matter how squirrely the function is. That's always true. I don't know how fast I'm going, I just know which direction I'm going. Does that make sense? I do actually know how fast I'm going. It's the magnitude, the height, but like we're just describing, not quantifying these things. Okay, so is this guy stable or unstable? Stable. Is this guy stable or unstable? Okay. So now let's think about the equivalent of this diagram. In this case, is more interesting. What if some people like to put the R on this direction. Some people like to put the X on this direction. It doesn't matter so much. It's how you interpret it. So here's our X steady state. Here's R. Oh, B. First call the parameter what I call B. Okay, B is positive. What do I have? Any steady states? No steady states. What happens when B hits 0? I have a half stable steady state. And is it stable on the positive x side or the negative x side? So I can draw a little circle here. And I can color it in on the bottom side. What happens when B gets negative? For every negative B, I'm going to have 2 0 crossings, right? And they're going to go out from that origin. If you think about it more slowly, it would be like the square root of B. So it has a curvature to it like that. This is just solving this, just plotting this function on its side. Right? Are these stable? It's going to be the solid dot for all that family of curves. They're all going to be stable, right? Because they're all going to have a negative x dot to their right and a positive x dot to their left. So this whole branch of solutions are stable. What about this whole branch of solutions? Unstable. So I would put a dashed line to indicate that one's unstable. This is a bifurcation diagram. We had no solutions for certain settings of the parameters, and then suddenly our solution bifurcated into 2 different solutions. And that's where the bi comes from, for the rest of the small parameters. Okay? Is everybody on board with how this works? So give me a B, and I can tell you what the qualitative behavior is. I've got a steady solution or unsteady solution. Give me a different B, no steady solutions. Give me another one, no steady solutions. And we could have had more parameters, like this one had both M and R. We could have had, added an A in here, and we could have done a lot more work to make this figure more complicated, but we could have always interpreted it that way. Does that make sense to everybody? So the qualitative behavior of one steady solution, one unsteady solution, the relative layout, the fact that the steady solution is at negative values of x, the unsteady solution at positive values of x, doesn't depend on the details. Does that make sense? Okay, let's draw another one that's even more interesting. What if we do x cubed plus b? And I'm going to write x cubed plus b. X cubed is, I don't want to draw it. I'm just going to draw it for you. What if I have one that looks like this? b equals 0 goes right to the origin. For b greater than 0 goes like this. B less than 0 goes like this. So how many steady solutions do I have for this b less than 0 case? This one? Is it steady or unsteady?
Stable or unstable?
Stable or unstable, sorry. It is, yes, is the answer. Is it steady or unsteady? Yes, it's steady. Is it stable or unstable?
Unstable.
Unstable, because over here we're going that way, and over here we're going this way. What about this one? How many steady solutions do I have? Just this one over here, right? Is it stable or unstable? Unstable. And if we think about back to this part, it's really just the slope as you're crossing the origin that's determining stable or unstable. If you're crossing with a positive slope, it's unstable. Crossing with a negative slope, it's stable. Okay, so what about this middle one? How many steady solutions do I have? 3. Unstable, stable, unstable. So what does my bifurcation diagram look like? What have I got for large positive B's? That's this one. I've got one unstable steady state. And is it on the negative side? So I'm zooming in. And then at a certain point, this one crosses. What happens when this one crosses? As B is getting smaller. When it just touches it, what happens?
Which curve are you talking about?
So it's in between this one and this one. For an intermediate value of B, but B greater than 0, this bend is just going to touch that line. So what will happen just when it touches?
It'll be like the half stable.
It'll be half stable, where the stable one is the smaller value of x, the unstable one is the larger side. It'll be at a positive value of x. So at a certain moment, we're going to get a bifurcation like this. And then at negative, we're going to get another one where this guy comes down and meets this guy. Looks like that. Like that. So in the middle values of B, we have 3 solutions: unstable at the highest x, stable at the middle, unstable at the lowest x. Up here we have only one unstable solution, it's at negative x, and over here we have only one unstable solution, it's at positive x.
You decide where it shifts from the stable to the unstable, like. you go
Yeah.
from
So as soon as they invented, you'll have to go through a half point. And then this one will disappear through a half stable point. And it's right when this guy touches, or when this guy touches. Does that make sense to everybody? So this one is just sort of drawing pictures. Let's look at another one that has an equation we can write down. This is called the logistic growth curve, and it's important for biology. So if I had a number of critters and they grow at a given rate, nothing else is the problem, what kind of answer do I get to that? What's my solution? It's exponential because it's a first order homogeneous constant coefficient equation. Is what we talked about last. But let's write down one that's more complicated. Now we've got a nonlinear term. It's kind of a mess. But we can still use these graphical approaches to understand how it works. So now we want to make a figure that's got n and n dot. And since this is the number of creatures, negative values aren't good. We're not messing. We shouldn't end up talking about negative numbers of creatures. That's a little odd. Not possible, whatever. We're gonna focus on positive n. So, how many steady states does this have? 2. 1 when n equals 0, and 1 when n equals what? Okay? So what does the function look like in between? If n is greater than 0, this is positive. And if n is less than k, is this positive or negative? Positive, so a positive comes a positive. So it's positive here, and then negative here. Everybody on board with that? I mean, it's a quadratic. You can think about it different ways, but just think about the zero crossings is a nice way to go. Okay, so I have a positive slope here. Is this stable or unstable? It's unstable. So it goes this way, above. And what about this one? Stable. So this is called the carrying capacity in the biological literature. And as soon as you have one creature, you take off exponentially, and you start growing exponentially. But then eventually you start approaching the carrying capacity, and you slow down your rate of growth until you reach the carrying capacity. If you start off with more creatures than the carrying capacity, they start dying off, and you come back to the carrying capacity. That make sense, everybody? So what does the bifurcation diagram look like as a function of k? N star k. Probably should be positive. Even if it's not, we can still think about it. So as k gets smaller, what happens? So where is this steady state for all values of k? It's always on 0. So we actually have an unstable steady state on 0 all the time. And what happens with this one? It's at positive n, and just gets bigger with k. So, presumably when it hits right at the origin, well, we're not thinking about negative n, so we don't have to worry about what happens. But that's the bifurcation diagram for that. And R gives you a rate, but it doesn't really change, interestingly, until R equals 0, right? Then, or R equals negative, then it gets really interesting. Flip sides. Okay? So we can try another one. Does everybody understand? See how this is going? So if I give you another differential equation, you can start thinking about how it works without much fiddling. Okay. So what's that one like? This one's a little trickier to think about at the beginning. So, at really large values of x, which term dominates? The negative x squared. So that means I have to be down on both sides. In the middle, we'll do something else. Not sure quite what. And what happens if x equals 0? The other one's equal to 0. So this is always a steady state. And if you think about it a little more, you'll see that there are like solutions like this, or like this. Or that's it. So they're, depending on R, you're either on this side with the maximum at positive x, or you're on this side with the maximum at negative x. Does that make sense, everybody? Okay, so is this stable or unstable? Maybe simpler. Is this stable or unstable?
That's stable.
This one's always stable. Is this stable or unstable? Always unstable. And what about this one?
Depends which function.
Right, it's the opposite of whatever that one is. So if it's this one, then this one would be stable. If it's this one, then this one would be unstable, and that one would be stable. So let's draw our bifurcation diagram. R, star. Okay. So we always have a solution at x equals 0, but it's going to change stability at a certain point. What value of R does it change stability for? Which is the one that's the half stable? It just touches it. R equals 0. And at that point, which side is it stable? And then on this side, so it'll be half stable on the positive x side. Okay, so what is it like for values that are bigger than for R is greater than 0? How can we think about that? If R is greater than 0 and x is greater than 0, this term is positive. This term is positive. So where is the maximum? So, yeah, you can write it this way. That might help make things a little clearer. So this has a solution at x equals R, and another solution at x equals 0. Does that make sense to everybody? So we put it over here. X equals R is a straight line. Now, which side is stable and which side is unstable? That's the next question. So if I'm over here at positive R is this branch. So the stable one is the one at bigger x than the one at the origin. Everybody following me? So that means this side is unstable. So there's a solution here at the origin that's unstable and a stable solution there. And what happens at the origin? Which one becomes unstable and which one becomes stable?
Can you take a step back? Because I thought you were just talking about the line that was x equals R, so where is the
Sorry. Yes. So this is the line that's x equals R. And so if x equals R, this is 0, which means x dot is 0. So x equals R is describing the other steady state, the one that's not the one at x equals 0. And then there's also a steady state at x equals 0. So here are my two steady states. X equals R, x equals 0. Now I'm trying to figure out which one's stable and which one's unstable. When r equals 0, we have the half stable case, where the quadratic is just touching the x-axis. When r is greater than 0, we have this one where this guy is stable and this guy is unstable. And then when it's this way, what's this curve like? So is this stable or unstable? Stable, and this one's unstable. So this is a different kind of bifurcation. So here we're chugging along in our bifurcation diagram with this unstable and a stable. We hit the origin, and which one is stable? The one that was unstable becomes stable, and the one that was stable becomes unstable. Does that make sense to everybody? So there's a whole lot of fiddling you can get through, but basically the whole magic is when we're looking at the steady states, we're really thinking about the roots of the right-hand side of that equation. So which root is stable and which root is unstable is talking about the derivative of this, because it's the slope as you're crossing through the origin. These kind of slopes are stable, these kind of slopes are positive. So that's the derivative of this with respect to x. That's giving you the stable and unstable bits. The roots, just setting this function equal to 0 is telling you where the steady states are. So we're basically setting this function to 0 and then thinking about its derivative at that same location. And that's what's giving us all this information. Does that make sense to everybody? And so we could keep making more and more complicated formulas, but it's always the same game. We're going to think about the 0 crossings, that is the roots of the right-hand side. We're going to think about the derivatives of those. And we could come up with really nasty functions like sine of x, which has an infinite number of roots, right? And half of them are stable and half of them are unstable. The ones where you're crossing on the way up are stable, and the ones where you're unstable, and the ones where you're crossing on the way down are stable. So we can get really nasty with the functions we prescribe, but they're all amenable to this kind of simultaneous phase space diagram plus a bifurcation diagram. So those tools allow us to analyze any first order, even nonlinear differential equation qualitatively, as long as we can plot the function. Does that make sense? So next time, we're going to start thinking about second order ones. And it gets a little harder because we can't draw everything all in the same graph. Suppose we had x dot and y dot. We might like to think about an x dot versus x figure, but we also need an x versus y figure and a y dot versus y figure. So there's a lot of things to think about. But it turns out we can think about that one in a relatively few kinds of diagrams as well. Okay. And this stuff is really fun. This is the thing that later, if you see a differential equation in the wild, whatever, I'm doing something, you can draw these figures right away, and then you'll be able to tell everybody how it's going to behave, and they'll be like, "How did you learn that?" And you say, "Well, it's just obvious from the equation. The equation told me what it wanted to do."